The title of this video lesson is It Remains to be Seen if x minus c is a factor. It's the end of section 4.1 polynomial functions, and I hope that by the end of this video lesson that you feel comfortable applying the remainder theorem, the factor theorem, and be able to recognize the connections between remainders and factors. And that's where the name of the lesson came from, the connection between remainders and factors. We're going to have a chance tomorrow in class to kind of practice some of these, but for the time being, take a look at this. Take notes as you feel necessary, and again, pause the video when you need to in order to jot down those notes. These two examples show long division examples. I want to review a little bit of the vocabulary with you. If you take a function, in this case f of x, and divide it by another function, we say that this function is the dividend. This is our divisor, and we get a quotient along with a remainder. So f of x is the dividend, h of x is the divisor, q of x is the quotient, and r of x is the remainder. And the same thing happened down below. The difference between these two examples, this one from yesterday and this is a new one, is that in the top example we got a remainder of 21, a non-zero remainder, and in the bottom one we got a remainder of 0. So let's take a look at the first one first, the top one first. We took a polynomial x squared plus 5x plus 7 and we divided it by a polynomial of the form x minus c. In this case, c was equal to 2. And if we happen to take a look at what we get when we evaluate the dividend f at 2, we'd get 2 squared plus 5 times 2 plus 7, which is 4 plus 10 plus 7, which is 21, and we notice that that's the remainder. Does that happen in the second one? Well, again, in this case, I guess we'd say that our c value is 5, because we divided by one of the form x minus c, where c is 5. So we're curious to evaluate f of 5, and f of 5 gives us 5 squared minus 6 times 5 plus 5, which is 25 minus 30 plus 5, and that's equal to 0. So looking at these two examples and using our inductive reasoning, we would say it appears that if a polynomial is divided by x minus c, then the remainder would be f of c. And it's what we call the remainder theorem. It's found in your book on page 244. And it's important enough, I think, to get down in your notes. Applying it to this example, if we wanted to find the remainder when x to the 87th minus 2x to the 36 plus 8 was divided by x plus 1, we do not, I repeat, we do not need to do long division or synthetic division, because if we did, we would have to insert a number of terms between these two, because notice the degree, we'd have to make up for the 86th degree and the 85th degree term and the 84th and so on, all the way down to the 37th. And then we'd have to do the same between the second and third term. Whether we did long division or synthetic division, we'd have to insert a bunch of coefficients in either variables with long division or no variables with synthetic division, but still it would be a rather wide-looking process, right? We'd have to use a wide sheet of paper. Instead, with the remainder theorem, we just have to evaluate the function at -1. So f of -1 is -1 to the 87th minus 2 times -1 to the 36 plus 8. And carefully evaluating our powers, the odd power would produce -1, the even power would produce 1, and -1 minus 2 plus 8 is equal to 5. So without doing any division, long division or synthetic division, we can find that the remainder would be equal to 5. And here's another example I'll just quickly go through with you. In this case, we want to know the remainder if you divided 2x to the 4th minus plus 4x cubed plus 5x minus 8 by x plus 3. No division needed, we just evaluate f of -3, which would be equal to, one term at a time, 162 minus 108 minus 15 minus 6, which is 33. Therefore, the remainder would be 33. So the remainder theorem, again found on page 244, serves this purpose. It's used to find the remainder when a polynomial is divided by x minus c. That's the use of it, and it's good to know that. You might want to jot that down. That's what the name kind of implies it. So the remainder theorem is used to find remainders. The other theorem from this lesson, important theorem from this lesson, is the factor theorem, which on page 245 is stated as follows. A polynomial function f of x has a linear factor x minus a if and only if f of a equals 0. So the if and only if means it's biconditional, so it says if this happens, if you have a linear factor of x minus a, then f of a will be 0. Also it means if f of a is equal to 0, then the function has a factor of x minus a. So if we wanted to show that x minus 2 was a factor, we can use the factor theorem. We would take f of x and evaluate it at 2. So f of 2 is equal to 2 cubed plus 5 times 2 squared minus 2 times 2 minus 24, which is equal to 0. So because of the factor theorem, x minus 2 is a factor of x cubed plus 5x squared minus 2x minus 24. Notice that this question, this example, had another question to it. It said another request, and that's to find q of x such that x minus 2 times it will be equal to that, the original polynomial. Well, what we're asked to find then is really the other factor besides x minus 2. Here's one factor, q of x would be the other factor. And that can be found with division. So using division, I would use synthetic division. You're welcome to use long division, but with division, you would find that the quotient is x squared plus 7x plus 12. And that would also validate the fact that the remainder is 0, because using synthetic division or long division, you'd find the remainder is 0. So I've already said what the remainder theorem is good for. This is what the factor theorem is good for. It's used to find factors of a polynomial, as the name implies. So if you think of what the name is, it will it will remind you of what the theorem is actually used for. So we've been able to make some statements like this in the last couple of days. R is a 0 of a function. R is an x-intercept of a graph of a function. X equals R is a solution or the root of a function f of x equals 0. That's kind of split up, but that says f of x equals 0. And x minus r is a factor of the polynomial f of x. What I'd like you to realize is that when one of these statements is made, the others follow. So they all say the same thing in their own different way. So if you know one of these things, you can conclude the others. They all say the same thing. And to illustrate that, here is a function, a quadratic function that's graphed. It's been factored. You can clearly see the x-intercepts are -1 and 0. So what else can we conclude? Well, because the x-intercepts of the graph are -1 and 3, excuse me, not 0, -1 and 3. The zeros are -1 and 3. That's what the zeros of the function are. The solutions to this equation are -1 and 3 if you set the function rule equal to 0, and the factors of the function's rule are x plus 1 and x minus 3. So here's one that is more typical of what you might be presented with. If you were given a function and you were asked to find the following, you'd probably begin by finding the intercept. So with your grapher, you'd enter this in your grapher. Go ahead and do that now and maybe pause the video. Now that you've entered it in your grapher, you could take a look at it with this window, and you'd see that the function kind of comes up like this, the graph, and turns and comes down, makes another turn and goes back up. And in the window, -10 to 10 in both x and y, this is what you see. And using your ability to find these zeros, you would find these three, which are -2.5, 1, and 5. So if those are the x-intercepts, then you can conclude three other things. The zeros are the same, -2.5, 1, and 5. It should be -2.5. The solutions to the equation, when you set it equal to 0, are x equals -2.5, x equals 1, and x equals 5. And the linear factors with real coefficients would be taken from these solutions, x plus 2.5, x minus 1, and x minus 5. And if you didn't want to have a rational number be one of our coefficients of our linear factors, you could rewrite that as 2x plus 5. Notice if you solve 2x plus 5 equals 0, you'd get x equals negative 2.5. The other ones would stay the same. If you were asked to find three polynomials of different degrees that have those as zeros, negative 2, 1, and 3, then again, if they have those as zeros, then they must have these as factors. X plus 2, x minus 1, and x minus 3. So those being factors, it gives you a little bit of flexibility to be creative. And I just came up with three different polynomial functions, g, h, and k. This is the simplest one. I just listed the three factors, and this would have a degree of 3. By making the degree of x plus 2 2 instead of 1, it keeps the same factors, the same solutions, same zeros, and the only difference is now this polynomial function h would have a degree of 4, where if you multiply these out, the leading coefficient would have a degree of 4. And I can add some coefficients. I added a coefficient to this third case, 5 as a coefficient. That would be the leading coefficient. And I added another factor, x squared plus 1, which doesn't have any additional zeros because x squared plus 1 has no zeros. You can't factor it. It would not cross the x-axis at any real value for 0, because we're only looking at this first part of this chapter as real zeros. We're only looking for the actual real solutions. We're going to look at complex numbers later on. So this polynomial has degree 5 and the same zeros. So interesting, we have three different polynomials here that each have the same zeros, but they have different degrees. The top one has degree 3, the second one degree 4, and the third one, k, degree 5. Which means that we can conclude that a polynomial of degree n has at most n distinct real zeros, because this one of degree 3 has 3, this one of degree 4 has 3, this one of degree 5 has 3. So we'll look at completing some examples and kind of consolidating this information in your own mind in class next time. Feel free to watch this again. Be prepared to come to class with any questions about this and any lesson from the past, and we'll see you in class next time.